Next question. Given below are two statements. Statement 1 is the electronic structure of atom in the second and third row of the transition metals always follow the pattern of the fourth row of the last row. And second statement is electronic configuration of palladium is krypton 401050. In the light of the above statement, choose the correct answer from the options given below. So it is wrong that the electronic structure of the atoms in the second and the third row of the transition metals always follow the pattern of the first row. In the transition metal series, all the elements in the first row, second row, and third row are independent. They do not have any common characters. So that statement is wrong. And the second statement, that is electronic configuration of palladium is krypton 401050, that is true. It is an abnormal configuration. In order to acquire extra stability to palladium, it will adopt this configuration, that is krypton 401050. So the option, that is statement 1 is false, but statement 2 is true, is the right answer here. So we can go to next question, that is in the complex is given here. FeH2O6 is a high spin complex that absorbs a light at about 100,000 nanometer, corresponding to transition between 5 T2G and 5 EG levels. The wave number of the radiation is. We want to find the wave number, but don't get panic when we see this question. The transition between the 5 T2G level and 5 EG levels has nothing to do with this question. We just want to find the wave number of the radiation, and it's given the energy of the radiation absorbs when the transition is happening. We just want to find the wave number of this radiation. So option A is 100 centimeter inverse, B is 1000 centimeter inverse, C is 10,000 centimeter inverse, and D is 1 lakh centimeter inverse. So we know that CFC in centimeter inverse is equal to a wave number, and the wave number is defined as 1 by lambda. We just want to find the 1 by lambda or the wave number in this equation. So if we want to find the wave number, it is given as 1 by lambda. So here it is given the wavelength of the light absorbed for this transition is 1000 nanometer. So we want to convert that nanometer into centimeter. For conversion, we want to multiply the nanometer into 10 raised to minus 7 if we want to convert nanometer to centimeter. So after we doing that, we will get this as it is equal to 1 by 10 raised to minus 4. 10 raised to minus 4. And when we take that 10 raised to minus 4 into upward, we will get 10,000 centimeter inverse. So the correct answer will be the wave number of the radiation absorbed for the transition in this complex will be 10,000 centimeter inverse. So our correct option will be option C. Next question. The observed magnetic moment of a complex is 1.73 Bohr magneton, the number of the unpaired electron in the complex. So the magnetic moment is given, that is 1.73 Bohr magneton. We want to find the number of unpaired electron in that complex. So option A is 0, option B is 1, and option C 2, and option D 3. So according to the equation, the magnetic moment mu is given as root of n into n plus 2, where n is the number of unpaired electron. So it is given that 1.73 is the magnetic moment. So 1.73, when we convert it into root, 1.732 is the value of root 3. So inside the root, the value will be 3, and we will get 3 only if n equal to 1. That is 1 into 3 will be 3. So when the n value is equal to 1, the number of the magnetic moment of that complex is equal to 1.73. 1.73. So the number of unpaired electron present in the complex will be 1. There is it is a very simple question. If we know this equation, that is when root 3, we have to get root 3, we have to take n equal to 1, and the number of unpaired electrons will be 1 here in this question. Next question. Given below, are two statements. One is labeled as assertion A and other is labeled as reason R. Assertion is the binding energy of the metallic lithium exceeds that of the Li2 molecule, though the Li distance is in the metal is 3.03 picometer angstrom, significantly larger than the atomic Li2 molecule, that is 2.67 angstrom. Reason, the bonds in the metals are weaker, but there are more Li bonds in the metal. In the light of the above statement, choose the correct answer from the options given below. So, correct option will be both assertion and reason are true, and reason is the correct explanation of assertion. So, in the metallic lithium, we know that it will not exist as a diatomic molecule, that is in the Li2 molecule. Rather, it will exist in the metallic form, that is there will be metallic bonds present in the, even though the binding energy for metallic lithium exceeds, it will be the more stable structure for lithium. And when we do the metallic radius, we are just considering the distances between the two nucleus of the lithium. So it will be high, that is van der Waals radius will be 3.03 angstrom. It will be significantly larger when we are considering the diatomic Li2 molecule, that is 2.67 angstrom. And the bonds in metal are weaker, but there are more Li bonds in the metal. It is also true that the bonds in the Li metal is weak, but there are a lot of Li bond because it can easily bind with each other when it is in the metallic form. So both assertion and reason is correct, true, and reason is the correct explanation of assertion. Next question given here is, given below are two statements. Statement 1, a solvent with a large autoprotolysis constant can be used to discriminate between a wide range of acid and base strength. And the second statement is, water have a leveling effect that brings all the strong acids down to the acidity of H3O+. In the light of the above statement, choose the correct answer from the options given below. Statement A, option A, that is both statements are true, and B, both the statements are false, and C, statement 1 is true and statement 2 is false, and option D, that is statement 1 is false and statement 2 is true, which is the correct answer. So a solvent, if a solvent have a large autoprotolysis constant, it can be used to discriminate between a wide range of base and acid strength, because water have a high autoprotolysis, that is it can easily convert to H3O+. So it can easily discriminate between a wide range of acid and base, and we can easily find the acid and basic strength of a lot of acids and bases when we are taking water as the solvent because of the large autoprotolysis of water. So that statement is true. And water has a leveling effect that brings all the strong acids down to the acidity of H3O+. So in water, we are considering the acidity of a acid on the ability of it so that it can produce H3O+ ions. How much H3O+ ion that acid can generate is the basis of determining the strength of that acid in water. So it is also true, water has a leveling effect that brings all the stronger acids down to the acidity of H3O+. So here both the statement 1 and 2 are true, and our correct option will be option A. Next question, the oxidation state of iron in hemoglobin is, we want to, it is a straight question from bio and organic chemistry, and we want to find the oxidation state of iron in hemoglobin, and the option A is +1, option B +2, and C +3, and D 0. So if we are if it is asking that the general oxidation state of iron in hemoglobin, we can easily say that the oxidation state of iron in hemoglobin is +2, but it is specifically asking that the oxidation state of iron in oxyhemoglobin, it will be +3, and in deoxyhemoglobin, the oxidation state of iron will be +2. So it is generally asked what will be the oxidation state of iron in hemoglobin. So it will be +2, and our correct option will be option B. Next question. Given below are two statements. Statement 1, the Stille coupling use tannates as the organometallic component. And in the statement 2, the Suzuki coupling involves organosilide as the organometallic component. In the light of the above statement, choose the correct answer from the option given below. Option A, both statement is true. B, both statement is false. And C option, statement 1 is true, but statement 2 is false. And D, statement 1 is false and statement 2 is true. So, in what is Stille coupling? In Stille coupling and in Suzuki coupling, this reaction is mainly used to form carbon-carbon single bonds. So carbon-carbon single bond is very hard to form. So these reactions are mainly used to form such carbon-carbon single bonds, that is sp3 bond between carbon. So in Stille coupling, it is true that the organostannates are used to bring one alkyl group towards the other. Here we can see the scheme of the Stille coupling below the options, and in the second we can see the scheme of Suzuki coupling. Here in Suzuki coupling, along with the alkyl halide, the organoborane component is taken in order to do the coupling between the coupling to form the carbon-carbon bond. So it is false that the in Suzuki coupling, the organosilide compounds are used as an organometallic compound. Organoborane compounds are used as the organometallic compound in Suzuki coupling. So the statement 2 is false, and the correct option will be C. That is, statement 1 is true. That is, in Stille coupling, organostannates are used, and but statement 2 is false. That is, in Suzuki coupling, organosilide compounds are not used. Instead, organoborane compounds are used for the coupling between two sp3 hybridized carbon. Next question. The point group to which CH4 belongs to. It is a general question and it is a theoretical question. If we are studying the group theory, we should be familiar with this question also. So if the CH4 group belongs to which of the point group? And it is a straightforward question. The point group of the methane will be tetrahedral, that is TD. And if naphthalene is given here, the point group will be D2H, D4H. So here it is given that what will be the point group of methane. So it will be tetrahedral, that is TD. Next. A particle is considered to be nano when its radius is in the region. So if we want to say that particle is in the nanometer, in nanoscale, what will be the radius of the particle? So A option, that is the radius will be 10 raised to minus 11 to 10 raised to minus 10 meter. B option, that is 10 raised to minus 10 to 10 raised to minus 9 meter. And C, 10 raised to minus 9 to 10 raised to minus 8 meter. And D, that is 10 raised to minus 8 to 10 raised to minus 7 meter. So correct option will be 10 raised to minus 9 to 10 raised to minus 8. And when we define a nanoparticle, we say that a particle will be in the nanometer range when its range will be 1 to 100 nanometer. That is when the range, when the particle have a radius range of 1 to 100 nanometer, we say that it is in the nanometer range. When we convert that nanometer into meter, we say that 1 nanometer is equal to 10 raised to minus 9 meter, and 10 nanometer will be is equal to 10 raised to minus 8 meter. So correct option will be 10 raised to minus 9 to 10 raised to minus 8 nanometer. Next question. The molecular orbital diagram for the C2 ion would show which of the following molecular orbitals. So we want to draw the molecular orbital electronic configuration of C2 ion, and the configuration is given here. So when we draw the molecular orbital diagram of C2 each carbon will have 6 electrons in them. So there is, if this molecule have a charge that is 2 so 2 additional electrons are also present here. So the electronic configuration of one C- ion will be 1s2, 2s2, 2p, 2px1, 2py1, 2pz1. So when they go under in order to form molecular orbital configuration, when they combine to form molecular orbitals, so the number of electrons will be 6 plus 6 plus 2, that will be 14. That is under and up to 14, they will follow this configuration, that is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, and sigma 2pz2. So our answer will be B option, that is the configuration of C2 2 minus ion will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p raised to 4, that is both x and y orbitals, and next sigma 2pz2, that will be the right answer. Option B will be the right here.